Today, I'm going to talk about this new subject, which we call the quantum Fourier analysis. And I think most people are familiar with Fourier analysis, and this has a long history. And actually, since the recent decades, there have been a lot of interaction between mathematics and physics, in particular the quantum theory in physics. So many mathematical concepts has been quantized, like quantum groups, quantum topology. And here we are going to quantize the idea in Fourier analysis, which we call quantum Fourier analysis. And in this talk, I will mainly talk about the general ideas, the framework, and with some examples. And I will not focus on the details of the mathematical definition or statements. We will show how this subject is related to different areas in mathematics, which may have potential applications in quantum physics. And in a recent paper, we gave an introduction of this subject. And this is a joint paper with Arthur Jeffrey at Harvard, Shennan Jiang at Hebei Normal University, Yinxiang Ren at Harvard, and Jinsong Wu at Harbin Institute of Technology. The paper is titled with Quantum Fourier Analysis. And we mainly discuss algebraic transformation, which is an analog of the classical Fourier transform. And sometimes this transformation has a pictorial meaning, like in the case of subfactor series. And we are interested in analytic estimates of the Fourier transform in the sense of Fourier analysis. And this will provide interesting tools to investigate phenomena like quantum symmetries appeared from quantum theory. Now, before we go to the quantum case, let's first talk about the classical Fourier analysis, and then we see how it revolves to the quantum setting. So in the early 1800s, Fourier introduced this transformation. It's given by integration of functions and called Fourier transform. The major idea at that point was to solve differential equations describing heat. And so given a function f on the reals, so let's say a Schur's function, and then we can define this integration and we get another function also on the real line. And this is the integration formula for definition of the Fourier transform. And this formula has several very good properties. First, given two functions on the reals, then using the additive structure on the real line, the group, and then we can define the convolution. And the Fourier transform is the relation between the multiplication of functions and the convolution of the functions. And that's the Fourier duality. And in particular, if we consider a differential equation, then the Fourier transform will change differential operator to a multiplication operator. And then solving differential equation becomes solving polynomial equations, which is much more doable. And that's a key point for solving those equations at the very beginning. So Fourier transform is a kind of a very good way to see some structures in a dual space, and the dual space may look nicer. And in this setting, the dual space is kind of a diagonalization of the original operators. Now, to get analysis additional to the algebraic Fourier duality, we can have a measurement. On the real lines, the natural one will be the Lebesgue measure. And then we can define the p norm of the function by this integration. And for p equal or b equal to 1, this is norm. And for p equals to infinity, it's the essential maximum. Then the Planchet formula said that the Fourier transform preserves the two norm. And from operator point of view, we can consider the function L2 function space as a Hilbert space. Then the Fourier transform is a unitary operator acting on the space. Now, to get the inequalities, just by definition, the integration formula of the Fourier transform is easy to show. The Fourier transform of f has maximum value bounded by the one norm of f. And then by interpolation methods, we can get the inequality for PQ norm, subject to the condition P inverse plus Q inverse equals to 1. So those two numbers somehow are due to each other. And then we get the inequality. the Q norm of the Fourier transform of F is bounded by the P norm of F. And this inequality was the classical Hausdorff-Yang inequality. So in this sense, we want to understand how the PQ norm are bounded under the Fourier transform. Well, in the general setting, the Fourier transform is not only considering the analytic estimates of the transform itself. For example, the following Yang inequality is also a classical one for convolution. So we take convolution of two functions, f1, f2. Then its R norm is bounded by the P norm of f1 and the Q norm of f2, subject to this condition, P inverse plus Q inverse minus I inverse equals to 1. So in this inequality, even though we don't see the Fourier transform, but once we study the convolution and its relation with the multiplication, say the P norm is defined by the multiplication structure. Here we are studying the R norm for the convolution. So it's relating the two different algebraic structures. So the Fourier transform is hidden in this, it's behind this inequality. So this is also kind of Fourier analysis in a general setting. Now we can go to a more abstract setting. That's we go from the real line to a group, and it could be non-commutative. And for convenience, we assume the group to be a finite group. And then different from the real line is dual is itself. For a group, its dual may be different. In particular, if the group is non-abelian, then the dual will become a non-commutative algebra. So to describe the Fourier transform, we can consider that as a transform from one algebra to another algebra. And here, we can say the first algebra is functions on the group with the discrete measure. And for the second algebra, it corresponds to the representations of the group. And there is one way, simpler way to define this algebra. It's the group algebra itself. So we can take the group G acting on L2 of G, the Hilbert space, and then the left action generates an algebra that's called the group algebra, denoted by LG. And then we also need a measure for this group algebra. And there is a natural one. So once we take the left regular representation, then the group elements becomes a permutation matrix. And then we can define the trace. And the trace will take 0 at non-trivial group elements and also and 1 at identity. So that's the usual trace of the matrix. And then with the two measure and the two algebra, we can define the Fourier transform. It's just the identification of the group elements, but from one algebra to another algebra. And then here we have the multiplication on the B algebra, the non-commutative one. It's the usual multiplication of matrices. And then we can use the Fourier transform, and that induced the multiplication as a convolution on the A algebra. And that coincides with the usual convolution on the A algebra as functions on the groups. And this is the usual way we consider the Fourier duality. But there is another way which is unusual. So we have the functions on group, that's the A algebra, and it has a multiplication. And then we can use the Fourier transform induce a convolution on the B algebra, on the matrices algebra. And then other than the multiplication, the usual multiplication of matrices, we will have a second multiplication, which we can consider as a convolution on B. And in this case, if we compute that explicitly, it will be the Hartmann product of the matrices, namely the pointwise multiplication of the entries of the matrices. Now, if we look at the Fourier analysis, like the two classical inequality we mentioned, the Hausdorff-Yang inequality and the Yang inequality. Then for functions in the A algebra, the usual one, we have the classical inequality. Now, under this Fourier duality, we can also consider those inequalities in the B algebra, in this non-commutative algebra. And then the P norm is also defined as a non-commutative measure. So it's a matrix, then we can look at the spectrum, the singular values, and then consider that as a function, compute the P norm. And in the infinite dimensional case, we need to do functional calculus to compute the P norm. And the interesting part is those inequalities are not only true on the A side, but they're also true on the B side. For example, the Young's inequality set, if we take the two matrices in the group algebra, and then we take the Hartmann product, pointwise multiplication, and then we can take this non-commutative R norm, it's still bounded by the P norm of the first matrix and the Q norm of the second matrix. So this is true but less obvious, and this is an unusual way to think about the Fourier analysis on the dual side. Now we can go further to generalize those group symmetries to probability group. The definition is similar to the group case. The major difference is that in the group case, the multiplication of two group elements give you another group element. For the probability group, the multiplication of two elements is a convex combination of other elements. So these coefficients are non-negative numbers and the sum is 1. So you can consider that once you take a multiplication of two group elements, it has a probability to become a third one. And then we can also consider the A algebra and the B algebra for this probability group. One is a functional group, one is the group algebra in a similar way, and started the Fourier analysis. And actually there's another important motivation to look at the probability group. It's a little bit stronger than this definition. It's called fusion ring. So where is it from? So if we have a finite group, like the permutation group has 3, then we can look at the irreducible representations of the group. Like for permutation group S3, it has 3 different irreducible representations. And then if we take tensor product of those representations, it will decompose, the tensor will decompose into direct sum of irreducible ones. So under the tensor product, those irreducible representations forms a ring called the fusion ring. And this looks like the probability group, except that the coefficients are not positive real numbers, but they are natural numbers. And up to a normalization, we can assume those, after normalization, the sum of the coefficient becomes 1. So it's almost equivalent to the probability group, but just the coefficients has a stronger condition. In general, the abstract definition of the fusion ring is the following. It has a basis x1 to xm of a z module, and x1 is a unit in this algebra. And the multiplication of two elements is a sum of elements in the basis with coefficients given by the natural numbers. And also for each element, it has an inverse corresponding to the inverse of group element, denoted by a star. And the coefficients like xj multiplied xk contains the trivial element if and only if k is the inverse of j in this sense. And this is the abstract definition of the fusion ring. So in general, the fusion ring doesn't have to come from a group. Now for this fusion ring of our probability group, we obtain, again, two algebra, which we call the Fusion Bialgebras. One is the functions on the ring or the group, and one is the group algebra or the ring algebra. It's defined in a similar way. And for the ring, we will have an additional scalar to normalize the multiplication, because its definition is slightly different from the probability group. And this scalar is called the Perron-Frobenius dimension. It's the unique positive character of the fusion ring. So once we have the two algebra A and B, and then we can define similarly two measurements. And one measure is given by the Perron-Frobenius dimension, and the other measure is given by the trace. But here, the trace is not the usual one. It's not the trace of the matrices in the B algebra, but it's defined as this. It's 1 at identity and 0 at other basic elements in the basis. Now the definition this way has several other motivations to get this. In particular, when the fusion ring is given by the representation of a group, then this dimension, the Perron-Frobenius dimension, is exactly the dimension of the irreducible representations. And with those proper measurements, then we can also define the Fourier transform as an identity map from A algebra to the B algebra. And then first one can check it preserves the two norm. So it's a unitary operator. And one thing we need to be careful is on the two different sides, we can get not only the multiplication, but also the convolution induced from the Fourier transform. And the convolution on the B side is no longer the Harman product, it's pointwise product of matrices. But still, we have two algebraic structure in the setting. And then next step, after we have the algebraic setting, it has two algebra with multiplication, with measurements, with Fourier duality, it preserves two norm. All the algebraic conditions are good. Now let's see what happened to the inequalities. So first on the A side, as functions on probability groups or fusion rings. On the A side, the Hausdorff inequality and the Yang inequality are still true. And the proof are actually pretty similar to the classical case. But on the B side, it's a bit surprising that the Hausdorff inequality, okay, it's true, but the Yang inequality is no longer true. So it seems like this is a very classical inequality, and the generalization is pretty reasonable from group to the general setting, like fusion ring or probability group. But even just this very natural setting, the Yang inequality doesn't hold. So something is wrong. And we can easily construct an example even for the three-dimensional case. That means the order of the probability group is 3. So then we can ask this question, for which kind of fusion ring this Yang inequality holds on B? At least we know that if the fusion ring comes from the representation of a group, then it's true. But in general, it's not true. So the very important thing is the following. If we just generalize the group on the algebraic level, then it's not enough. We need one additional quantum condition. For example, if the group is a quantum group, then this is true. And another situation is a half algebra. Like if we want to understand the group algebra, the algebra itself is not enough to study the group, but half algebra is enough. It remembers the group structure. So in general, there is a set called weak half algebra. And if we want the analytic structures, we need a positive measurement. And it's called a weak C-star half algebra. And then in functional analysis, there's another setting. It's called subfactor. So both N and M are operator algebras or phoneme algebras. It's infinite dimensional. And if we just look at one phoneme algebra, we can study very interesting non-commutative like probability theory or harmonic analysis on that. Now here, if we have two algebras, then we not only have harmonic analysis, we can even add a Fourier duality with Fourier analysis. And one side is from N, the other side is from M. And we'll talk about later what do we mean by a subfactor. This is an infinite dimensional structure that provides quantum symmetries. And the third way is from looking at the quantum symmetry from topological point of view. So if the ring, the fusion ring R, has a unitary categorification, and then in other words, that means this gives a 12-Weyer's 3-manifold invariant. And in this case, the Fourier analysis works, the inequality holds. And since here we require the quantum condition on this general setting, so we call the inequality the quantum inequality. And here we are considering the quantum Yang inequality. And in particular, once R has a categorification, and the corresponding category is called the unitary fusion categories, and R is the Gross-Nicker ring of the unitary fusion category. So in this setting, R has a good algebra with good quantum inequalities. So quantum becomes a major feature that once we add a quantum condition, then those inequalities are true. And if we don't add a quantum condition, but just generalize the algebraic structure, the inequality may not be true. So the failure of this inequality becomes a very good analytic obstruction of unitary categorification of the fusion ring. This is actually very important because to show the categorification of the fusion ring, it usually requires solving a lot of equations called Pentagon equation with a lot of variables. But here we have a very good analytic abstraction to show this categorification, to solve the categorification problem. And actually, besides the Yang inequality, there are other versions of quantum inequalities, like which we call quantum Schur product theorem or quantum sum set estimates, and so on. And all those inequalities provide such kind of analytic abstractions. Now let's take an example. So first, as a special case of the Yang inequality, we have it's equivalent to another condition called the Schur product theorem. And in the quantum setting, what they said is that if we have two operators, then their convolution is still positive. So why we call that Schur product theorem? So if you consider the two operators as functions, then okay, it's easy to see the convolution of two positive functions should be positive. But if we look at the dual set on B side, then it's that for two positive matrices, and then we take Hadamard product, it's still positive, and that's the classical Schur product theorem. But in the general setting, this is a very abstract convolution. It's no longer the Hadamard product. But still, in the quantum setting, we can show the AI algebra coming from a quantum symmetry like subfactors or quantum group of the examples we mentioned above. Once we have two positive operators, their convolution is positive. And this is more or less equivalent to the Yang inequality for the case PQR equals to 1. But even for this kind of very elementary inequality, it's already very powerful. It's applying this theorem to the dream field center of the unitary fusion category, we can derive the following theorem. This is in joint work with Sebastian Paco, Jinsong Wu in recent work. And it's that suppose we have a unitary fusion category, okay, and it has a Gaussian ring. And for simplification, we assume the ring is commutative, but in general, it doesn't have to be. In the commutative case, we can diagonalize the fusion ring and get a character table. It's similar to the group case, but here it's probability group. And then we have the character table lambda ij, and it said the following: if we take the multiplication of three columns after normalization, then it has to be positive. So for the group case, the denominator, this dimension is 1. So we only see that's the multiplication of three characters and then take the integration. And that's exactly the structure constant for the group case. And it's always a natural number. And here in the general setting, it's kind of a quantum analog of the structure constant. And we can show it's always positive if it comes from this quantum symmetry, like the Gaussian ring. Well, this inequality may not be true in general on fusion ring. So this particular inequality is an analytic obstruction of categorification. So here is one example that it's a ring with rank 7, like a generalization of all the 7 group. And the proof from this dimension is kind of a generalization of the order of the group. And just for this ring, the following 7 matrices are the fusion matrix. It tells us when we take multiplication of 2 elements, how it decomposed. Like the first matrix is the identity. And then we can compute its character table. It's just linear algebra. We get this 7 by 7 matrix. And then algebraically, to show whether this can be categorized, then we need to solve the Pentagon equation. And for rank n, like rank 7 case, the number of equations is about like 7 to the 9, and the number of variable is about 7 to 6. So in general, it could be very challenging to solve such large family of polynomial equations, higher degree actually. But here we have a very quick way to show this example has no categorification. Just by checking this Schur product criterion, we take the last column and take the multiplication 3 times and normalize by the probabilities per dimension. Then we get a negative number. But the Schur product criterion side, if it can be categorified, this value has to be positive. So this is a very easy analytic estimates. It's easy to check just using linear algebra. But as a consequence, we know this ring has no categorification. And actually, just this single example has been open for several years. And it passed all previous known number theoretic obstructions, algebraic obstructions. And it has been challenging to solve those polynomial equations. But now we have a new way to get a new analytic obstruction to rule out this example from categorification. And actually, this is not the only example. Just from a classification result, we can get 34 of such kind of fusion rings subject to certain dimensions. It's actually pretty big. It could be like 1 million for rank 5 case. And from the 34 simple integral fusion rings, 4 of them are from group case, so they can be categorified. While for the remaining 30, most of them pass the previous known criterions. And using our new analytic ones, we can rule out 28 out of 30 just by applying this Schur product criterion. So it's about 93%. So this is quite surprising to us. It's very efficient criterion. And actually, it's very easy to check. Since this is just linear algebra, we can easily run a code, and it only takes a few seconds to get the results. So this has been a very successful application of the quantum Fourier analysis to show how to eliminate those fusion rings from categorification. But the more important thing is to show those inequalities are really quantum. If we do not use the quantum structure, then we may have counterexamples such that those quantum inequalities are not true. So quantum conditions are pretty essential behind the analysis. And actually, when we prove those inequalities, we do need those quantum conditions. We will see how we use them first at the beginning in subfactor theory. Now let me give more information about the subfactor theory. So there has been a long history about subfactor theory, and a highlight is the discovery of Jones polynomial. It's not invariant from subfactor, from modern subfactor theory. And that happened in the 1980s. So what's that? First, a factor is a von Neumann algebra with trivial center. And if it's infinite dimensional and it has a trace as a favorable measure, then it's called a type 2-1 factor. And the example of that will be the called hyperfinite. That means it can be approximated by finite dimensional von Neumann algebras. And it's the infinite tensor product, for example, infinite tensor product of 2x2 matrices with the usual trace, normalized trace, and under the GNS construction. And this can be regarded as a kind of matrix algebra on the 0-1 interval, somehow non-commutative interval. And von Jones at the beginning got a lot of interest on this example, and he tried to classify the size of relative size of two factors, the n in n, and we call this pair a subfactor. And one example of such pair is that if we take n to be the factor and like the infinite tensor product, and then it admits action of permutation groups. And under the cross product, we get a bigger factor n. And then the relative size will be exactly the order of the group. And then it's remarkable result from Jones in 1983 that in general, the relative size, called Jones index now, doesn't have to be integer. It could be any number from 4 to infinity. And more interesting than under number 4 is quantized. And this quantized phenomenon is closely related to the quantized phenomenon in quantum physics, the quantum field theory. And now for our talk, from this kind of pair, we can deduce two bimodules. Like for M, it's an algebra, and N is a subalgebra. So M itself has a left multiplication by N and a right multiplication by N. So it's a bimodule. And then if we look at all the bimodule maps on M, this forms algebra. We call it A. And there's another way to switch the role of N and M, like the Fourier dual, then we get algebra B. And in particular, if the subfactor comes from this group cross product, then the A algebra is exactly the functions on the group, and the B algebra is the group algebra. So that's the setting we talked at the beginning of free duality and free analysis. Well, in subfactor theory in general, this group doesn't have to be a classical group. We can consider a general subfactor is a cross product by a certain quantum group, even though it may not be really a quantum group. So this is some general quantum symmetries. And in this way, we can look at this group in a very general way and look at the two algebra. And furthermore, we can study the Fourier analysis in this setting. Unlike the close connection between subfactor theory and knot invariant, Jones introduced a pictorial language called plane algebra to study those algebras. And in particular, the A algebra can be represented by a picture on plane, a planar picture with 4 legs. It looks like a square. And then in this algebra, the usual multiplication will be just a composition of the square-like picture in the vertical direction. Well, since it's on the plane, it's very natural to consider the horizontal composition as well. Then one may ask, what's that? Then, okay, here in this talk, you can guess it must be the convolution. And actually, indeed, it is. If the A algebra is given by functions on group, then the first diagrammatic composition is exactly multiplication of functions. And the second one is convolution. And another interesting feature is 90-degree rotation. So this 90-degree rotation, pictorially, it intertwines the horizontal direction and the vertical direction. And it's actually it plays the role of the Fourier transform. It intertwines the multiplication and the convolution. So that's the pictorial Fourier duality. And actually, not only this condition, for classical Fourier transform, it has another condition. It has a periodicity 4. And here, the single rotation is 90-degree rotation. If we rotate that 4 times, it's a 2-pi rotation. So it's an identity map. This also coincides with this algebraic property of the Fourier transform. And furthermore, in subfactor theory, we have this unique trace. It gives you a measure. So we can also study analysis. And actually, the inequalities we mentioned above, like the Hausdorff inequality and the Yang inequality, they all works in this quantum setting. Now here, I will give you one proof, and the only proof in this talk, for this quantum Schur product theorem. So the one we applied to get this analytic obstruction of categorification. Actually, the proof is very simple, but the proof is very intuitive. I will show you why we need a quantum condition. In particular, we actually need topology in the proof. So if we represent those operators in this diagrammatic way, then the convolution is a horizontal composition. It's a square-like. And since x, if we assume x and y are positive operators, then we can take the square root of this operator. And the multiplication is the vertical direction. So we decompose that as a vertical composition, and we get a second picture. Now the interesting part is we can cut the picture in the middle. Then the bottom is the mirror image of the top. And this mirror image corresponding to the adjoint operation in operator algebra. So that means the second picture is the operator multiplied its adjoint. But this operator is not in the A algebra neither in the B algebra, it's in another bigger algebra. But still, since that's operator algebra, we have this positivity. And another important feature is this topology, the role of topology in this proof. So if we take this composition, it's a convolution. So the convolution itself is given by the composition of these two parallel lines. And once we cut it in the middle, then we have a single horizontal line on one side. So somehow we cut the operation of the convolution by half. So this is a very unusual operation in the in the classical science. But in this quantum setting, this is in general, it follows the idea of McCarthy called topological quantum field theory. In this more general quantum setting, we can cut the convolution as half, and then we can prove the positivity in a quite different way. So this kind of quantum setting does provide new tools to understand the classical inequalities, like positivity. Because subfactor theory has pretty wide connection in mathematics and physics, like at the beginning operator algebra, and then quantum group representation theory. And the remarkable point is knot theory, where we get the Jones polynomial. And then later the lower dimension topology, category theory, and some other topics in physics. And here we are adding one more dimension to this wide world. We are looking at the quantization of the Fourier analysis, and from subfactor theory as a bridge, we can reach to other areas. Like in this way, we first prove those inequality on subfactors, and then using known connection, we can translate the inequality on fusion category and dream field center. So we get analytic obstructions. And this is a picture of my advisor Wang Jones, and when he won the Fields Medal at 1990. But unfortunately, Wang passed away last year. But I think his work is still going on, and we are expanding this very beautiful theory on subfactors. And subfactor is the main quantum symmetry we are considering. And actually, because of this wide connection, we can also transform the quantum symmetry to other settings, like the infinite dimensional Katz algebra and locally compact quantum groups. And for locally compact quantum, actually it's more subtle, since this is no longer type 2. We need to consider weight instead of trace. And this becomes much harder. And also in the topological setting, we can extend those planar picture to higher dimensional. We can look at not just planar algebra, but surface algebra, or even higher dimensional manifolds. And in general, the unitary topological quantum field theory with defects. And also those structures are closely related to the categorical setting. And furthermore, it's also closely related to the structure in quantum information or condensed matter, like the structure of tensor network or multi-body system. So those are the quantum symmetry we are studying, and the inequality can be transformed from one symmetry to another symmetry. And also, other than the inequality we mentioned, we actually consider several others. In particular, we have several interesting uncertainty principles. And we also characterize the extreme measures of those inequalities. And those are uncertainty principles are actually quite interesting. So at the beginning, the Heisenberg uncertainty principle is already from a quantum theory. But somehow the underlying symmetry is given by the real line. So here we can change the underlying symmetry from the real line to a more general quantum symmetry, and then get a quantum uncertainty principle in that sense. It's kind of more quantum. And those uncertainty principles actually leads to very interesting new insights. In particular, the entropic one can be understood as entanglement entropy in quantum information, and we can get a free duality in that way to understand maximum entanglement phenomenon. So kind of two directions. One is a more general symmetry from the classical symmetry real line to the quantum symmetry, and the other direction go from inequalities like Hausdorff inequality, Yang inequality, to more general inequalities, so kind of two coordinates in this framework. And now, besides proving those inequalities, we actually also provide some new inequalities and new phenomena. Like the central limit theorem is very important in the classical Fourier analysis. Somehow it's said it can be translated to another statement. Like if we take a positive function and we repeat the convolution, and up to a proper normalization, it converges to a Gaussian function. Well, in this setting, if we look at the planar picture, the convolution is a horizontal compensation. So if we consider 2D renormalization, then we can both compose the picture horizontally and vertically, and then repeat that. So it kind of expanded to a 2D lattice, and then we repeat this process. And then actually we can show in the subfactor setting, if we repeat this process, then given an operator x at the beginning, finally it will converge to a very special operator called back projections, started by Dietmar Bisch. And for the group case, it corresponds to the subgroup of the group, constant function on subgroup. And for subfactor case, it corresponds to intermediate subfactor, so the analog of intermediate groups. And then we can show, starting from any elements, then automatically it just converges to such subgroups or intermediate subfactors. In particular, for Z2 case, we only get two special subgroups. One is the trivial group, one is the full group. And that's corresponding to the two different Z2 order of the Ising model in that sense. And also, we can consider phase transition this way. So that's another interesting perspective. And mathematically, we can propose an interesting question on the real lines. So instead of start with an abstract operator, we can look at a very concrete Schwarz function, let's say a positive function on R, and then repeat the convolution and the multiplication. And we consider this is kind of 2D central limit theorem. And the conjecture is this limit will be always Gaussian function. And actually all the Gaussian functions are fixed points of this map. But still we cannot prove this result. It looks kind of a basic statement at the beginning, but we tried pretty hard to prove, but still we cannot get it. And we actually check this by computer. We start with a pretty random function at the beginning, and it converges to Gaussian function in a very quick way. So far, it's a conjecture, and I think that could be a very good conjecture for people who are working on Fourier analysis. And one concept reason why this block map will converge under the block map, why the function should converge to Gaussian function, because the Gaussian function minimizes the entropy of f plus the entropy of its Fourier transform. This kind of entropy has been studied by Hirschman and Beckner in sense of uncertainty principle, and the minimizers are Gaussian function. So we have a stronger conjecture that under that block map, this entropy also decreases. So eventually the minimizers are Gaussian functions. And this question is even open for cyclic groups. We don't know the answer for cyclic groups for this. And using those analytic methods, we are able to solve some other open questions in subfactor theory, also apply the analytic methods in the classification of subfactors. So at the end, I will just have a quick, give you a quick view of the perspective of this subject. Actually, we are not only considering those inequalities. In modern analysis, we also look at the inequalities in families, like the Brascamp-Lieb inequality. It has been studied for 40 years. And this inequality is very rich. It has parameters given by linear transformations. And it includes several classical inequalities. By taking special linear transformation, the inequality already includes like Yang inequality and Hausdorff inequality. Yang inequality and Herder inequality. It also includes some other geometric inequality like Loomis-Whitney inequality. And this is a very rich topic. Now here, from the quantum point of view, actually, we can also propose a quantum analog of this inequality, which we call the quantum Brascamp-Lieb. Now the key point is that all those compositional pictures can be considered as a cobordism in topology, in particular in topological quantum field theory. And those cobordism correspond to linear transformations. So we can replace the linear transformation in Brascamp-Lieb by those cobordism, and then we have a topological analog. So we replace linear transformation by those cobordisms, and we can replace the quantum symmetry R. We can replace R by quantum symmetry A. And more mysterious part is this magic condition, like P inverse plus Q inverse equals 1. This magic condition in classical Fourier analysis has a topological meaning, and that corresponds to the Euler formula in topology. So the most basic part, P inverse plus Q inverse equal to 1, corresponds to the most basic equality in Euler form, in topology, that's Euler form. So we believe there should be much more coincidence between analysis, the quantum symmetries, and topology. And that's the part we want to explore for the future. Thank you.
So did you say that you made a sort of serious attempt to extend things like Brascamp-Lieb to this context?
Yes, yeah.
And you have some special cases of it, such as the ones that you mentioned, but it's just the completely general version that has not yet been achieved.
Yeah, it's not been achieved, and it's pretty general version, and the Hurd inequality, the quantum version, and the Yang inequality, they are all special case of this general quantum Brascamp-Lieb. So it has the same favor. And and even the Loomis-Whitney, another case, also fits in this framework. And actually recently, we can also show the quantum Loomis-Whitney. So there are some evidence this framework work. But there's one interesting part that doesn't show up in the previous setting. That's the role of topology. And one hint is that the topology has relation with this extra condition, P inverse plus Q inverse equals 1, this kind of condition. And this is kind of magic. We don't know why, but we check several examples we know, and it just works in that way. And we believe in general there are more topological behavior behind those inequalities. In particular, there is actually one conceptual reason. Brascamp-Lieb has a very deep geometry behind the inequality, or the geometric condition between those linear transformations. And here we have those topological conditions between those tangles. And I believe that will play a big role in this quantum analog.
Well, Martin Lindsay records his thanks for a beautiful talk. I would certainly like to agree with that sentiment. So thank you for presenting these this wide range of exciting new ideas.